So the first question is, are there any more questions from last time? See, now you've had the introduction to my lectures from George a couple days later. Yeah. Yeah. Did you say M? Yeah, M was a matrix. It was a transformation. So we had the generic system of differential equations you get. This could lead to chaos. Was we had a vector of integrals. In the example that I gave of the two-loop massless double box, planar double box, like I sketched out the dependencies of the integrals on different ones. Well, I think I also mentioned the non-planar double box. And so what you're supposed to write here is all the different master integrals after you do the reduction. And we had two master integrals, or the procedure returns two master integrals associated with this topology. It has, it returns two associated with this topology. And then it had some daughter topologies, like this one, D-box. There were a bunch of other ones down here. Anyway, that's what this I vector is supposed to represent. And I started writing out one of the differential equations for a p-box, and that would have been one of the matrix elements of this A matrix, where the coefficients are rational functions of the kinematic variables, which in this case were s and t, and they also depend on epsilon. So I'm just reviewing that I wrote this equation down, and then I discussed the fact that you might want to change bases on here. And that's where this matrix M entered. I wrote, consider a new set of bases, J. If we know this equation in one basis, we can find another equation, analogous equation in the J basis. So you plug D in here, and then it acts on, D as a differential operator can act on M and gives a J, but it can also anti-commute past here and give a M on DJ. And this is DI, so it's also equal to AMJ. So you can now solve for DJ. You have this equation here. You can multiply by M inverse, and that will isolate DJ. And when you multiply on the left by M inverse, you'll see that there's a inverse AM. Minus a M inverse DM, all multiplying J. J's are also master integrals, but there's an ambiguity whenever you get master integrals. They're different choices. And the matrix M is supposed to indicate some generic transformation from one basis to another, because some bases simplify the differential equations. So this, we can make it look, well, here's the claim is it looks like this, but here's A prime. It's the thing sitting in front of J in this equation. So this is A prime. The thing in brackets, okay?
At some point you reach this epsilon factorized form from this.
Yeah.
This step seems kind of.
I didn't explain this step. It's not even known how to solve it in general for arbitrary number of variables. There are some techniques for trying to do it in the one variable case, I know. I don't know even what the status is for proving how to do it in the two variable case. So it involves, let's say, something scientifically we call fiddling around. And so the main notion is that if you put it into that form, then everything's going to simplify because you're going to sort of decouple the equations. And there are some cases where it's known that you can't put it into this form. In other words, when you do D on the top level masters, you return the same thing. And you get coupled systems of first order equations instead of having ones that separate in this epsilon parameter. And when that happens, sometimes you can't separate them at all, and then the system isn't solved by these multiple polylogarithms. It gets solved sometimes by more complicated things like elliptic polylogarithms. But in the case that led to a lot of developments in the 2010s, these were all reducible to multiple polylogs. If you can do it, then you can get MPLs, but it's not guaranteed that you can do this. Any other questions on that or from anyone else? Okay. Anybody else? So, I said yesterday we were going to switch to n equals 4 today, but I slightly lied because there was something important I wanted to say that is also applicable to the real world or to QCD or other things, which is that it's a kind of a slogan that, cross sections are loop integrals too. And there's a technique sometimes called reverse unitarity. And it was sort of shown how this works by Anastasio Melnikov. So as we were discussing in the first lecture, if you want to do a complete QCD calculation, you need to be inclusive to focus things at short distances. And that means you need to include the real radiative corrections as well as the virtual corrections for a given process. And I sketched out the anatomy of that for jet production. Let's do a process that's a little bit simpler, which is the one they studied here in this paper, which was Higgs production. in PP goes to Higgs plus X. It would be extremely similar if we were doing inclusive Drell-Yan production, like George was just talking about. Anyway, the dominant Higgs production cross-section is gluon fusion. So that starts off at leading order through this Feynman diagram where you produce a virtual top quark pair, which then using the large top Yukawa coupling makes the Higgs. But the top is quite heavy, and it's a pretty good approximation to consider it to be much heavier than the Higgs. And then we can integrate it out. So similar to SMEFT with new physics, we can do this standard model Higgs coupling with integrating out the effect of the top quark. And when you do that, you get to summarize the interactions as H times the gluon field strength. This operator. That's what this X means. This is a dimension 5 operator. I think when Ilaria was doing it, she would have written it as phi dagger phi times G times the same thing, because she wanted it to be invariant under the SU2 cross U1 gauge group. But we're working in the broken theory after this has become a VEV, and we're looking at the radial part of the Higgs. So we just usually write it like that. Anyway, you take this operator, and this is the heavy top approximation to this. And at leading order, you can write this interference graph. And that represents the Born level amplitude for glue to Higgs squared, and work out that matrix element. And one of the features of that is that the gluon invariant mass, the two gluons coming in, by momentum conservation, exactly equals the Higgs mass squared. And then we have the NLO corrections, and they include virtual corrections. For example, a gluon exchange here, which is then interfered with the lowest order one. And then we have real corrections, where we make a Higgs, but we also make another parton. There could be quark lines in here, but like I did in the jet case, I'm just ignoring the quark contributions. But they're always of the same form, and the same techniques apply to them. So this is how we wrote the interference graphs for real radiation here. Notice that SGG is MH squared here, but over here, SGG is greater than MH squared, because you're producing the center mass energy squared has to be enough to produce MH squared and one more recoiling massless particle. So we usually write that SGG is MH squared over Z, where Z is between 0 and 1. And in the virtual corrections, Z is equal to 1. So the challenge is to evaluate the total cross-section in perturbative QCD to higher orders. And we're going to take advantage of the fact that it's a very inclusive thing, the total cross-section. So it depends on very few scales. In fact, the only scales it really depends on are SGG, the incoming energy, and the mass of the Higgs. And all complicated functions can only depend on dimensionless arguments, so they're really just functions of Z. So now we want to look at this graph, for example, or just to go one further. At n, well, I'll just write down an n and a low double real graph. Anyway, just so you get the idea, we're drawing these interference graphs. And now we want to stare at them, squint at them until they look like loop graphs, okay? So just kind of ignore for a second that this was here. This looks like a two-loop planar double box integral, kind of written vertically instead of sideways, right? Now there's a couple of differences. One is that when we were looking at those double box integrals before, these were independent momenta, K3 and K4. But this is an interference graph. So the stuff on the other side, it's just the conjugate of the amplitude over here, and it has to have the same momenta. But if we kind of treat things in an all outgoing momentum convention, we call this minus K1. To put it another way, we take the forward scattering graphs. We think of it as forward scattering for GG goes to GG, which can have a Higgs cut, where we can cut the Higgs line, which I've always done here. I've cut these lines, okay? You also cut various other lines, but how many you cut depends on whether it's virtual or real. So you have to consider all of them, but the rule is you have to always be able to cut one Higgs line. And what do these cuts do? They impose on the massless lines delta p squared equals 0 for the gluons and any quarks if I put them in there. And delta p squared minus mh squared, delta p squared minus mh squared for the Higgs line. But maybe we can treat these delta functions a lot like propagators. In fact, there's a formula for 1 over x plus I epsilon, which is, this thing, if you ignore the epsilon, it looks like 1 over x. You just have to be careful what's going on here, and you find that there's a principal part prescription that you need to specify for the real part. And then there's an I pi delta of x that controls the imaginary part. You can rewrite the imaginary part of this as something like I epsilon over x squared plus epsilon squared. So it looks like a delta function as epsilon goes to 0. And this is the normalization of it. So we're going to use this equation or think of using it backwards. We're going to write 1 over x, we're going to write the delta function as 1 over x plus I epsilon minus 1 over x minus I epsilon. And then we should divide by, I guess, 2 pi I. So everywhere we see a delta function, we're just going to insert something. If I set x equals to p squared minus m Higgs squared, I'm going to get the Feynman propagator. And then I'm going to get it a second time with a relative minus sign with the opposite I epsilon prescription. And then you're going to say, now this thing looks just like a loop integral. It's just instead of a single propagator here, I always have to have in my mind I have two different propagators with opposite signs and opposite I epsilons. But when you go through all the integration by parts technologies, the I epsilons, we never really saw them. Well, I deleted them, but you never really would have seen them anyway. And so all the differential equations have a very similar structure for these cross-sections reinterpreted as loop integrals. So maybe that went kind of fast. Are there questions about this? So you can reduce these integrals down in the same way that we discussed. But in some sense, it's even easier because a lot of boundaries vanish. So you consider these integrals with general powers for the propagators. But like in that double box example we had before, when we had set some propagators to 0, we collapsed them down to these smaller topologies, right? Now consider what happens if we have a integral, which is a double box integral, like from over here. And suppose this leg goes to 0, has its new I goes to 0. At this point, we remember that this was really a delta function that's supposed to keep this propagator open so that there's a real particle there. So because of that, the new I goes to 0 boundary is always 0 for these guys, the ones that cross the cut. So those boundaries vanish on cut lines. And then you'll get after doing the integration by parts, you'll get other integrals which don't vanish. For example, you'll get this sunset master integral, where this is a Higgs line, and these are gluons. And this integral is basically the integral over the full three-body phase space without any Feynman diagram contributions at all, because it just represents these cut propagators which convert the loop integral into a phase space integral. So essentially, you can use all the integration by parts technology and differential equations to solve this problem as well. And the differential equation part you can derive because what you want is differential equations in z. The whole answer is just some function of z. So you want to take some of these integrals and compute d by dz. But it's easy to compute the partial with respect to mh squared of 1 over p squared minus mh squared plus I epsilon minus you just get and then you treat this as just any other doubled propagator. So in the original graph, you would have had nu h equals 1. Now it's doubled to nu h equals 2. That is the exponent of the propagator got doubled, and you derive these reduction relations, and you reduce it back to some nice set of masters. So you can recycle all of the loop technology that we talked about to handle cross-sections too, if the cross-sections are simple enough. If they're very complicated, like they have experimental cuts of P jet has to be smaller than 30 GeV, forget it. But for things like the total cross-section and some other distributions, simple distributions, you can use this technology. Any questions about that before we sort of dive into applying similar mathematics to n equals 4? If the cross-section is complicated, well, in the first lecture, I said that there's this sort of general set of tools, which I didn't explain in detail, but they go under the general heading of subtraction methods or slicing methods. Those things are designed to make the differential cross-sections for infrared-safe observables finite. They require a lot of work to develop the algorithms, but once you have them, then you can apply them to very general sets of observables, and that would be the method you would use for something with complicated, realistic experimental cuts. So the general way these things work is somebody first develops analytic tools like this to compute a total cross-section at the next order in alpha S, past where it was done before. And then people start to relax and make the cross-section less inclusive. Because at a hadron collider, no experimentalist can measure the total cross-section, because it includes things where the Higgs went too far forward to make it into the detector. And so you need to start putting in realistic cuts. You can make some guesses based on the K factors, but yeah, question?
So what is the motivation to do things like this if you anyways have to do the IVP on differential equation stuff? Why don't you just take the matrix element and then square it afterwards, where you can get to the double number of loops, for example, then?
Well, so this is designed to do the phase space integrals with real radiation. And it might also have virtual corrections as well. So quite often you already know the matrix elements, but you don't know how to integrate them. But if you want a simple enough observable like the total cross-section, then you can use these analytic tricks to do the integrations. And you can push them, this is not as hard as doing an arbitrary 3-loop integral, because these momenta are not separate. So it's not like doing gluon-gluon scattering. It might be a little harder because there's a mass in there, but it's actually much easier because there's only 2 momenta, external momenta in the problem. I don't know, did that answer your question, or?
Yeah, I guess so, yes.
Okay. Yep.
So you did this for the effective field theory, something like the top part.
Yeah.
So, and you said that these differential equations, like solving the method, is used for such simple cases. So, if I go to the full theory where I don't integrate the top.
Yeah, you could, that's a great question. It just gets much harder because instead of a local operator which produces polynomial Feynman rules, if you do that integral over the top quark, you get some arc cinch or something. And that doesn't play as well with this IBP approach. So yeah, most people who have included the full top quark effects, they're down by at least a loop or more compared to the heavy ones, and they do it not in such an inclusive way, but they break things up into pieces and they put in realistic cuts. I think maybe, but what you can do is you can expand to higher orders in 1 over m top. And that has definitely been done. As you go to higher powers of 1 over m top, you introduce higher dimension vertices, which put in higher order polynomials from the matrix elements. But that's not a big step past this one. It means you have to reduce higher tensor loop integrals, but it's the same topology. So you can like run the same program a little bit harder. But if you really want to do it exact in the top mass, I'm not aware if people have done it this way. Maybe some have, I'm not sure. I think they mostly broken it back up into pieces again. Any other questions? So we defined these G functions last time as particular kinds of iterated integrals recursively if you differentiated this with respect to x, you would get another G, it's A21, divided by x minus A1. Or we could multiply this by dx, and this would be dx over x minus A1, which is d log of x minus A1. Now these indices could also depend on the kinematic variables. They might not be constants. And maybe you want to differentiate these functions with respect to them too. And it's a little trickier then when you take derivatives in here, but you can use various identities to rewrite them in terms of other d logs. And so an alternate definition of multiple polylogs is through not an integral definition like this, but it is a differential definition. And in many ways, it's more convenient. So we know that these guys here have a weight, which is n, and it's a single integral over something that's weight n minus 1. So let's instead try to define functions f, which have weight n. By proposing that df is a sum over a finite set of things we call sk, and these sk's can depend on our underlying variables. There's some function of them. And we want the differential to be a sum of a finite number of d logs of some functions, rational functions of the x's, hopefully rational. And so we call these the symbol letters. And letters belong to an alphabet. So this is called the symbol alphabet. And then there's another notion, which is a so when we have functions, there are products on functions that say that f times g maps, so these might belong to some function space. And so you can map from 2 copies of the function space to 1 copy by multiplication. You take one f that belongs to the space and another g that belongs to the space, multiply them together, and so that's called multiplication. But there's another thing that's called co-multiplication. And so there's a notion of being able to have a coproduct, or sometimes it's called a coaction, because it's not exactly a product, but it's a map from a function space to two copies of the function space. And the map that does this is called delta. And delta can be graded. So delta can be a direct sum. Delta acting on a weight n function can be split into q's that go from 0 up to the weight. And this splitting is according to what happens on the, what the weights are of the two things on either side of this tensor product. So this is all very fancy mathematics, but the most important thing is, for us, is the n minus 1 comma 1 component. And for that differential over there, we just take this form here, actually, and we copy it over here. But we treat it as a tensor product so that the stuff here lives on kind of one space and this lives on another space. And this logarithm, sk, has weight 1. And this object here, because we've differentiated something that had n integrations, has weight n minus 1. So we often call the FSKs the n minus 1 comma 1 coproducts. So they are nice transcendental functions that appear as coefficients of different d logs when you take the derivatives. Yep?
I'm sorry, sir, but I cannot follow. Like, what are we trying to do here? Just
We're trying to construct something called the symbol of the function. And this is the first step in doing it. And it's basically trying, the whole idea is to try to simplify these multiple polylogs, because there are many possible arguments and many integrals in different directions, and they're not all independent. Like yesterday, I mentioned that there's a shuffle relations, so that some of them are related to each other. So the thing about the symbol is it sort of expresses the functions, all of its derivatives, in terms of logarithms. And assuming you know all the relations between all the letters, then you know all the identities between logarithms. There's only one identity. The log of AB is the log of A plus the log of B. That's like the only identity you need to know. So then once you've kind of reduced everything to logarithms, you kind of know all identities for these very complicated multiple polylogs, and it makes it easy to simplify them and to know when different ones are different or the same, and so on. And it's the scaffold for building back up the answer. So you can also write a very complicated function, not out explicitly, but you can write it in terms of its first derivatives. But then you might not even want to specify the first derivatives because they might be too complicated. So then you can take their first derivatives, and we write that this way. This is exactly the same formula as this one, but I've applied it to something called FSK. I put that index in the back, and then I introduce a new index, SJ, that comes from the different d logs here, and I put that one further forward. And then I call this thing the n minus 2 comma 1 comma 1 coproduct, because I first kind of differentiated once, and that one becomes a logarithm at the back. And then I do it again. So I'm simplifying everything down because these functions are becoming lower and lower weight. I'm going to go n times right now. Yeah. The one in the front will be a pure logarithm. So, in fact, we can do the last step right now. You set me up perfectly for it. So the delta 1, 1, 1, 1, 1 n times of f is just a big sum over SI1 to SIN of f SI1, comma, whoops, SI2, comma, SIN. Tensored with, and now I'm just going to do one slight change of notation. So I just did exactly the same thing. I just kept iterating this. The only other thing I did was I dropped the logarithm. Because when I define something called the symbol of f, it's understood that all these things are logarithms, and we don't want to just keep writing logarithm all the time. So instead, we just write these arguments. Any other questions? So that is the symbol operation on a function, and it was introduced by Goncharov, Spradlin, Virgu, Volovich in 2010. So I should say these things up here, this was the logarithm, but we kind of wrote everything as coefficients times the logarithm, and these are rational numbers, these coefficients here. Some cases they just if you normalize things right, they're all integers. So the symbol is just a set of rational numbers as coefficients of this big tensor.
And it can always we can always do
If you have something that's multiple polylogs, those kinds of functions. If you have something that's elliptic polylogs, people have been introducing something called the symbol prime to deal with it. So there are other analogous notions that go beyond multiple polylogs, but this is the simplest thing for multiple polylogs.
it can always be done.
For multiple polylogs, yeah.
For any complicated kind of argument, like any kind of argument in a polynomial, and you
Yeah.
can write in the tensor product of log.
Yeah.
And this
Sometimes when you do it, the letters will be not rational. And then you might actually get the symbol first. And it might be multiple polylogs, but the letters might be irrational. Or they might have complicated relations. So it's not always totally obvious how to recover the full function from the symbol. But yeah.
Is this mostly useful for this
You can imagine that you didn't reach the epsilon factorized form, but you still had some guess about what the symbol letters were, and you could plug that ansatz into the guess. But it wouldn't be a uniform transcendental weight. So you might have to plug in at each power of epsilon some rational function of the kinematics times these functions. But you could try to solve it that way if you couldn't find the epsilon canonical form. But it would be simpler to, what's that? I did it before the canonical form existed. I had differential equations. I just made a guess of what the functional form was, and I solved them, and I didn't get them in canonical form. So it's possible, but it becomes increasingly hard as the problems get harder and harder. It becomes much easier if you can find such a form. Well, you also have some clues about how to do it, because some of the integrals, if you're in a theory, even if it's not n equals 4, there might be n equals 4 integrals that have the same topology. And these integrals turn out to be, have nice properties. So you might be able to kind of do some guesswork based on that.
So if you have some polynomial, let's say, of order diagonal, so if you just simplify its argument, let's say you get zeta. So where you will put zeta? Because
Did you say zeta 2?
Zeta,
Yeah. We lost all the zeta 2's when we did this. We lost them all. Because for this function of a given weight, we took as many derivatives as its transcendental weight. And one of those derivatives wiped out your zeta 2 that you want. How do you get it back? You can go to boundaries. So, okay, since you asked that, let me first give you a simple example. Do you remember the definitions of the classical polylogs? I showed you the harmonic polylogs before. This is an even simpler case. I think I may have mentioned it briefly, but you just integrate over the previous one, and Li1 of x is minus log of 1 minus x. So let's rewrite this in differential form. So d Lin of x is Li n minus 1 of x times dx over x, which is d log x. So we go look at this rule here, and we plug in Lin of x, and we see there's d log x. So this is Lin minus 1. So, sorry, I think I should have written one more formula, which is that S of f is S of f sk tensor sk. In other words, this was an iterative definition of the symbol, but you can also implement it one step at a time by taking the derivative, and you put the last, the d log argument here, and then you keep going. So then the symbol of Lin of x is the symbol of Lin minus 1 of x tensor x. And then you keep doing it for n minus 1. And then that gives you another tensor x. And then at the end of the day, you're left with a logarithm, and there's an overall minus sign, which sits out front. So this is the symbol of Lin of x. Okay, now I'm going to come back to your question. Suppose I take the symbol of Li2 of x, and I add to it the symbol of of this. So that ends up looking like this. Now I have to tell you one other thing, which is that the symbol of log x, log y, I can do a d log x or a d log y, and that will give me a y at the back. And then the thing in front will be log x, so I'll just write it like this. But because of Leibniz rule, you can also take the d of log x first, and then you'll get a y in the front. So the symbol of log x, log y, it has these two terms, x tensor y and y tensor x. So this is the symbol of minus log x, log 1 minus x. So you might know that there's an identity that says that Li2 of x plus 1 minus x is minus log x, log 1 minus x, plus pi squared over 6, zeta 2. Okay, so I could see all of that identity through here, except the pi squared over 6, or the zeta of 2. So how could I do that? Well, I could go to a boundary. Suppose I take x to 0. The Li2s, these guys, by the way, have a regular power series expansion around x equals 0, which is x to the k over k to the n. So Li2 of 0 is 0, but this gives me Li2 of 1. This is simple because when x goes to 0, log of 1 is 0, and it kills this even though it's divergent. So basically, you have to work out a boundary and know what Li2 of 1 is, okay? But it's a simpler problem than the full x dependence. Yeah. 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 But you just sort of need to know it at one constant, so at one point. So to say it another way, these, first of all, I would say that the symbol is a starting point, but you can actually work with the n minus 1 comma 1 coproduct instead. And then in terms of this coproduct, over wherever up there, it's equivalent to the first derivative in all directions. So you know all derivatives, all first derivatives. So then you just have to specify the boundary value at one point, because you know how to move in all derivatives. So if you can fix boundary values at one point, not just at the top, but for the sequence of functions that build up your function, that's the way to keep track of all the constants. Any other questions?
This case, you have this multiple logarithms, and there you have your simple alphabet being only x, 1 minus x, then
Yeah.
x minus 1.
Yeah, that's right. I should have mentioned that. So the symbol alphabet for LIN is x and 1 minus x. So this is the alphabet not only for this case, but also, so it's the alphabet for LIN of x. But you could also put in things like x over 1 minus x, because those can sort of be built as combinations of log x and log 1 minus x. And so there are a bunch of other things in this. And in general, it's really this set of HPLs that we talked about last time with just zeros and ones. There are two to the n of these. And each one corresponds to whether you take x or 1 minus x in each slot. It's in one-to-one correspondence with the HWs, where these were zeros or ones. So you have a binary choice at each slot, and you get 2 to the n of them.
And so factors which are not of this form?
There are many other functions where this works. I mean, I also mentioned -1. That's a very simple extension where now you have a 3-letter alphabet. And then we're going to get to the Higgs form factors, which we may not get as far as, but there's this 2D Dalitz plot as a function of dimensionless ratios in a 3-body decay. And many of the perturbative results involve a symbol alphabet that has U, V, 1 minus U, 1 minus V, 1 minus U minus V, U plus V. So this is another example. These were originally called 2D HPLs by German and Ramidi, but they also fall in the general, multiple polylogs with symbols class. Any other questions?
So you say that in general we only need the case 0 and 1 for this way, then we don't need the case -1. But in the
It depends on the problem. For these HPLs with 0 and 1, you have 2 letters. If you need -1, you get this one. So like for the DGLAP evolution kernels, you need these for virtual, but for real contributions, you need these guys too. You might even need elliptic stuff at high enough orders. Depends on the problem. For the 2 goes to 2 scatter, the big challenge is trying to figure out what the right alphabet is. One approach is to do the differential equations for specific integrals. The other approach is to guess, which I like.
And the other question is, when we, let's say, as you say, try to identify the alphabet, to say it's not easy, but the number of components of the alphabet is easier to identify, or is, there is some rule that say you need 2 or 3 or 4 components, and you guys put out the components, or
In the general case, it's hard.
also you don't have any idea on the number?
There is some one way to try to get to the symbol alphabet is there are some tricks that the symbol alphabet is associated with where the singularities of the integrals are, and this is an old problem due to Landau. So you can do some Landau singularity analysis. So that's one. So how to guess the symbol alphabet, or determine, would be better. So one is to do the integral. And that often, when it's hard, means do the IBPs plus the differential equations. Another is to do Landau singularity analysis. Now the issue with the Landau singularity analysis is that it gives you points in phase space. It tells you where letters vanish. It doesn't directly tell you the letters. It tells you where they vanish. So you can check that something's consistent with the Landau analysis, but whether you can really prove that that's the only possibility, it's not completely obvious to me. There's also, a lot of these integrals have some kind of projective representations. And there's something called Schubert analysis. And it's done in some other space, like some momentum twister space. So you will see some pictures that have a bunch of lines intersecting in various ways in papers on Schubert analysis. But I've never really done it myself. So anyway, those are some things.
Number of symbol alphabets. There is no relation between number of symbol alphabets and this weight of your function. There is no relation, right?
So the statement about the weight, as far as we know, the weight is always less than or equal to 2L, where this is the loop order. So if you're at one loop, you're at weight 2. And then you can pretty much show everything as dialogues. If you're at weight 4, 2 loops, you get to weight 4. But you don't know that the symbol alphabet that works for a 2-loop problem, if you add a loop, it might not work anymore. It depends. But there's a few simple cases in planar n equals 4 where we just guess that the same symbol alphabet works to all orders. And we know it works to 8 loops, so we think it's going to work to 9 loops. But there are more complicated cases where it's not clear what the next order symbol alphabet is going to be. Yeah. Oh, let me just mention one other property of the symbol, which is this shuffle. I mentioned the shuffle algebra operation in the last time for HPLs, but the general statement is if you have 2 functions, f times g, to get the symbol of f times g, you can take and you know the symbol of f and the symbol of g, you can do this shuffle on s and g. So that means you write out s and g in terms of these big tensor products of s's, of these symbol letters. And for each term in f and each term in g, you just multiply together the 2 rational numbers in front of those terms, and then you shuffle all the terms. So you interleave them, but you keep the ordering the same for all the ones that came from f and all the ones that came from g. It's really a consequence of the Leibniz rule for differentiating, just applied many times. So we've been able to push to very high loop orders by finding simple problems in a toy theory that has some resemblance to QCD, planar n equals 4. And I just wanted to sort of sketch how that goes for one of the 2 cases where we've been able to get to the highest orders. It's actually very closely related to, so there's a n equals 4 super Yang-Mills planar analog of glue to Higgs glue, where we can work out the finite parts of the amplitudes to 8 loops. So it's not exactly the same. It's really a matrix element of some operator O2 with 3 gluons that have momentum K1, K2, and K3. So we can call this thing F3. Well, this might be some finite part of it. So it depends. So if we have this, and O2 is the trace of G mu nu A self-dual part. So it's not exactly the same as the glue-glue coupling to the Higgs. For this operator O2, the plus guy vanishes. And the minus minus guy is non-zero. Whereas for the Higgs, the Higgs couples to the same thing without the self-dual. This could also be written as a trace of g mu nu times g mu nu plus, or g, let me just write it as g squared plus gg dual, I think, with some number there. Anyway, when you add this gg dual term, it breaks parity, and so in the Higgs case, you get the same coupling to plus plus as to minus minus. And the other cases are forbidden by angular momentum conservation. This one is chiral. It only couples to this one. Now, you might ask, why are we doing glue to operator 2? G, why don't we just do the Sudakov one? This process. Well, this thing has only one scale, which was SGG. So it would have some minus 1 to the L epsilon by dimensional analysis. Then after that, it could only depend on epsilon. So we don't have any multiple polylogs. We have no functions for it to depend on. That's no fun. Plus, techniques don't really work. The techniques involve taking information from one part of the kinematics and moving it to another part of the kinematics and combining information from different limits. And here we have no limits, so we can't actually do anything. What we really do is we construct the answer for a finite version of this where we've factored out all the infrared singularities that are in this thing. So we know the finite answer to 8 loops, but we don't even know what the divergences are past about 3 or 4 loops. But we can still look at the finite part. So as I was saying, I think I already erased it. For this problem with 3 gluons, we have U and V. So there are 3 momenta, K1 plus K2 plus K3, add up to minus the Higgs momentum. If we take the square of this equation, it tells us that S123 is mh squared. And we could take it to be, it's not really a physical particle here, so we could take it to be space-like if we want, or time-like. And then 2ki dot kj is Sij. And S12 plus S23 plus S31 is equal to S123 because the ki squareds are 0. If we then divide by S123 to define some dimensionless variables, we have this equation. And we're going to call U S12 over S123 and V S23 over S123. And then W is 1 minus U minus V. But it's useful to keep it hanging around because there's a dihedral symmetry that permutes 1 to 2 to 3 to 1, and it cycles U, V, and W into each other. But this is the kinematic plane in terms of U and V, and this is the decay region where you decay to 3 gluons. And this is a scattering region over here with mh squared space-like. And then there's a time-like scattering region down here and in these regions. So that's the kinematics. And if you just do one loop integral, which shows up in the one loop amplitude, which has one external mass in it. And it's like gamma of 2 plus epsilon times this integral over the Feynman parameters. And it has a minus, terms of the Feynman parameters, as a minus S12, A1, A3, plus a minus S23. A2, A4, plus a minus S1, 2, 3, A4, A1, all raised to the 2 plus epsilon. So you can do this integral with the same change of variables that I gave in the first lecture or second lecture for the massless box. And you will find that instead of just getting logarithms like we found for the all massless box, you'll also find a dilogarithm, and you will find a dilogarithm of you'll find Li2 of 1 minus 1 over u plus Li2 of 1 minus 1 over v plus some logs. And this was for the case where the Higgs was, or the operator was sitting here, and 1, 2, and 3 were out there. But you're also allowed to cycle these guys around. That also contributes to the amplitude. And when you do that cycling, well, this will become a 1 over v, this will become a 1 over w. So now let's compute the symbol of this Li2 of 1 minus 1 over u. According to the rules over here, we take and we put 1 minus 1 over u in the back, because that's x over here. And then we put minus log of 1 minus the argument over here. So that's a 1 over u. So if you have a symbol that has a AB in it somewhere, you can replace it by A and then B. That's just because log AB, these really stand for logs. And log AB is log A plus log B. So you need to know all the identities between all the different symbol letters, but once you have that, you can pick a canonical form, and you can use these rules to reduce things down. And also, if you have a constant out front, and then somewhere you have a 1 over A, then you flip the sign of the prefactor when flipping over the A. Just because log of 1 over A is minus log of A. So this thing could be rewritten as plus u tensor 1 minus u over u. Well, this is really u minus 1 over u, but I can flip the sign. You can flip the signs inside arguments, because log of the negative and of A and log of A are basically the same, up to an I pi. But we're not tracking any constants right here. And then this would also be, through this rule, u tensor 1 minus u tensor u. So you can rewrite this thing a few different ways. But if you like u and 1 minus u, you see that they both occur. Both these symbol letters occur in the symbol of this dialogue. So we can say that the symbol alphabet at one loop has a U, and then by cyclic symmetry, when we permute, well, there's a V. We also get a W, and then we get these guys too. Yep.
So my question is like, these polylogs are very valid, like in the if argument is negative or less than 1, but they just blow up like in positive, right? So
No, they're valid in both regions if you analytically continue them. You can use them in that entire plane. But they will develop imaginary parts.
yeah. So
Yeah.
Like otherwise they will give it will give a imaginary part. So how you are tackling that, because it's sometimes double imaginary can give you zeta 2 and you cannot figure out where it is coming from.
Yeah, that's a great question. It's in this region here, in the middle, this is pseudo-Euclidean. All the letters are between 0 and 1. And if you look at all the integrals, they all are defined with a Feynman parameter denominator that is manifestly negative definite. And you can pull out an overall minus. And after that, they have like no singularities in the middle. And so apart from some overall factors that have to do with things like minus, take out some scale, there's some I-pi's associated with this, then it should be a real function in this pseudo-Euclidean region. So you can, and you can find representations of these that are perfectly fine in this region. And then you have to do an analytic continuation to cross this boundary. And the way I do it is I don't try to do it everywhere at once because I'm not a phenomenologist. I don't have to predict it at some random point here. But I know what the answer is on this, on some of these lines. So like this one is HPLs with zeros, ones, and minus ones. And I know how to use the shuffle algebra to put all the ones that transform non-trivially when I do this analytic continuation. I know how to put them into explicit logarithms. And then I just transform the logarithms, and I know everything that's happening in here, and then I know everything that's happening just on this side of the boundary here. And then I use the differential structure to integrate up everywhere else. So this differential structure, if you know how to do the analytic continuation at one point, you can use it to get the answer anywhere else. And that's sort of what's also done in pheno applications. So these pentagon functions, well, anyway, there's other cases where people do something similar. They use the differential equations to integrate up on different branches of the kinematics.
But this thing you can check only if you know some information about arguments, that it is what is the nature of that argument. But
Yeah, before you can do this, you need to know the symbol alphabet for your problem and to structure things like
but
this.
beforehand you don't know like what is this argument it can be like. After, let's say you got symbol, but you don't know it's going to be positive, negative, how complex it is. You don't know. Like,
Well, the vanishing of the symbol alphabet tells you where all the interesting things happen. So these 6 letters, this is the V equals 0 line. This is the U equals 0 line. And this is the W equals 0 line. So this is the only place, the only other possible place you could get branch cuts, get something non-trivial happening, is on 3 other lines. This line here is U equals 1. This one's V equals 1. And down here is W equals 1. Now you also know from the structure of the problem that you should not get branch cuts in the physical regions on these lines. They should only involve logarithms that open up at threshold, and we have only massless particles except for this operator, and that tells you where the branch cuts appear. Since we're mentioning this is called the branch cut constraint, and this branch cut constraint in this bootstrap is an important one, and it says that the first entry of the symbol cannot be all 6 of these letters, but it can only be U, V, and W. And once you've imposed this constraint, then when you go and look at your function space, it's very smooth near these other ones. Okay? So like the classical polylogs, they have x's and 1 minus x's in their symbol. you might expect them to have branch cuts at x equals 0 and also x equals 1. They do have a branch cut at x equals 1, but they have a regular power expansion around x equals 0. And the reason is that the first entry is 1 minus x. And the first entry controls the locations of the singularities, and it's whenever it vanishes, because it's like a logarithm. There's a cut when its argument goes to 0. So there, you can read off from the symbol where you have to pay attention. And here you have to pay attention at x equals 1. There's a cut in the complex x-plane at x equals 1, but it's totally regular at x equals 0. Sometimes you can get some power suppressed logarithm, but anyway. Yeah. Any other questions? So the name of the game here is to guess that one loop is all you need to find the symbol. Well, okay, people had calculated 2 loops too, and they found the same symbol alphabet. So then you get more confident. If nothing changes from 1 loop to 2 loop, maybe it'll be the same to an arbitrary number of loops. So as far as we can tell, that turns out to be the case. But you can't write down any old tensor in these 6 variables because it's a multivariable problem, and we have an integrability condition which comes from the equality of mixed partial derivatives in 2 variables. We didn't have that condition in this HPL case because that only had 1 variable. There are legitimate HPLs for all 2 to the n cases of x and 1 minus x in any combination. But here you can't put any letter next to any other letter because you have to impose this integrability relation. Let me just first write down explicitly for this symbol alphabet what the derivative of any function of u and v is. So it's from this formula sk partial of log of sk partial u. So letter u, that has a d log u, log u with respect to u. That gives a 1 over u. And then there's the letter 1 minus u gives us a 1 over 1 minus u with the minus sign. And then there's the letter w, since this is 1 minus u minus v, it has a u in it that we can differentiate, and we get a 1 over 1 minus u minus v, which I'll just write as w again. So I'm just writing out, in principle there are 6 terms here, but the v and 1 minus v, when I hold v constant, they don't contribute, so I get these 4 terms. And there's a UV symmetry, so I can write down the same equation just by swapping the roles of u and v. So here's an exercise for you to do because I'm running out of time. You want to take d squared f du dv and subtract off d squared f dv du. And you can write it as a sum over ci cj of the, and these can be rational functions of u and v, and they will depend on the double coproducts. Here we saw some single coproducts in the first derivative. When you take the derivative of df dv with respect to u, you'll use this formula. But in this term, you'll have a v sitting in the back, and you'll put some other stuff in front. By the way, I gave a set of lectures on this a couple of years ago during COVID, and the slides from them are on the web, and you should be able to find them if you search for Mainz amplitude games. So if you were interested in this stuff, you could go there for some more details. And there's some various other papers around I can tell you about if you want. But anyway, when you take this difference and require that it vanishes, it gives you some constraints. And the exact constraints, you have to analyze this as a rational function of u and v. But let me just illustrate one constraint. You're going to get a term with f of 1 minus u, 1 minus v. And it's going to have a singularity as v goes to 1 from here and as u goes to 1 from the next derivative. And when you do it in the opposite order, you're going to get the same singularity in the denominator. And so this is one equation that you're going to find that you have to satisfy. Oops, sorry. Thanks. Actually, let me define, so I don't make the same mistake again. I will define f of x, y with a kind of commutator symbol to be this combination. So I didn't do the complete analysis. I just looked in the region u goes to 1 and v goes to 1, and I noticed that none of the other terms are singular in that region except these two. And so when you analyze this in that region, you have to find that the terms that you get from doing things in the reverse order have to cancel. And so that's one of the integrability relations.
You won't find FUV minus FUV.
There's another one similar. I'll show you what it is in a second, but it's not quite as simple. So I can also use the dihedral symmetry to conclude that f1 minus u, f1 minus v is 0, plus cyclic, which means u goes to, I can cycle these around. U goes to v, goes to w, goes back to u. So that's really three equations. And then you ask for one with involves the commutator of u and v, and there is one, but you have to add 1 minus w with v. And that's 0. And then here you can add dihedral symmetries, which include cyclic and also flip, and you get 6. So there are 9 integrability relations. This is what we call these relations that come from the equality of the mixed partial derivatives. Now we found that we found empirically that there are more pair relations. So we found that in fact f1 minus u, f1 minus v without the commutator also turned out to always be 0. So we found this to be the case in planar n equals 4 super Yang-Mills, this problem, to 8 loops. But we also found it to be true in both the integrals that you need for planar and non-planar n equals 4 super Yang-Mills to 2 loops. And some 3 loops. Well, other people noticed some of this. But it's not clear that it holds for all 3-loop amplitudes. It appears not to hold for some 3-loop integrals. But amplitudes are special combinations of integrals, so we don't know. And then we found some other relations, but they're actually better described if we change alphabet. So just to say, an alphabet is not exactly a fixed thing. You can do linear changes of variables, linear in the logarithms, or rational. So like you could take u over vw and you could call that thing b. And you could then cycle those relations and get some other guys like this. And then you could, if you want, instead of using 1 minus u, you could use 1 minus u over u. Anyway, when you write these down, you find more relations like FAD equals 0 and FDE equals 0. And then, so there's a large set of relations that resemble the integrability relations but are stronger. And they're not totally understood from first principles. And anyway, when you put these relations in, you can start to build up the space of functions. And I'm running short of time, so I'll just say that we could build the space of functions that satisfy all of these extra relations up to about weight 8. So we could do it.
Is there any advantage of using these variables?
Advantage of,
Advantage of using these variables over that one?
yeah, because it makes like some of these relations simpler. You could write these would have corresponding equations in the other alphabet. They would just be longer. It's just everything gets more compact when you make these kinds of relations as simple as possible. In fact, since you asked, let me just write out the answer in this n equals 4 theory. So at one loop, the symbol is one term in this alphabet, but then you have to add cyclic plus flip, the dihedral symmetry. So it's really 6 terms. And this symbol was written in the other alphabet a while ago, but it was a lot longer. In this alphabet, it's 2 terms plus cyclic and flip is 2. Now, the 3-loop one is 636 terms. So I've decided I'm not going to write it for you today. But if you want, come back in a few years and I will write on the blackboard the 8-loop symbol, which is 1.67 times 10 to the 9th. I mean, I can give it down to the last decimal place, but last integer. So I didn't really have time to explain in more detail how the bootstrapping works, but there are these definite rules that you have to obey, and from that you can construct these spaces systematically. You can do it at the symbol level, you can do it at the level of these coproducts. And then you write an ansatz, or a guess, that's a linear combination of these functions. So you have some functions fi that live in this space. And I should say that you just take them from the weight 2L part of the space. This is one of the miracles of n equals 4 super Yang mills. The only ones you ever need are those which have exactly weight 2L. Doesn't happen in QCD, for example. And then you take limits where you know what's happening. And so in these limits, you end up getting constraints on these unknowns Cij. You get a whole set of equations where you sum over the unknowns. And if you have enough equations, you can uniquely determine all the coefficients. And it helps to have friends who know what's happening on the boundary, so they can tell you what the boundary conditions are, and that helps to fix everything. And so that's why we could go to this order. And there's a lot of things you learn when you go to this order. You can see the finite radius of convergence of perturbative QCD, not perturbative QCD, of perturbation theory in this theory. It actually has a finite radius of convergence, which is different from QCD, which is an asymptotic series. And you can see that kind of emerging numerically when you plot the ratios of the 8 loop to the 7 loop. It looks extremely flat, and it's sort of, everything's trying to go to the same point. And then there are amazing relations between different quantities in this theory that involve reversing the symbol and writing it backwards, as well as applying some map on the letters. And they're totally bizarre and not at all understood. So anyway, I leave you with that to ponder, and thanks for your attention. Happy to take any last questions. Yeah.
Why it is possible in these n-equal experiments to go to a group so easily?
Well, the bottom line is that it's an integrable quantum field theory. It's kind of strange. There's some kinds of integrability that are not allowed to happen above 2 dimensions. But this is a different kind, and it happens. But there's a 2-dimensional theory lurking underneath, which is kind of a world sheet of string theory, because there's an ADS-CFT duality that relates this to a string theory propagating on anti-de Sitter space. And the boundary of the anti-de Sitter space is Minkowski space, and that's where you scatter the gluons. But people realized a while ago that there are a whole bunch of conserved currents in this game, enough to, in principle, solve the problem. And it's certainly behind a lot of the miracles we see, even if we don't use it too explicitly. It's used more explicitly by the people who provide us with the boundary data. They have a more concrete picture of this string or flux tube, they sometimes call it. But they also, they make some assumptions, it's not really from first principles. But their assumptions are completely different from our assumptions. And then we check them against us at every loop order. And things work very well.